Hello, everyone. Happy New Year and welcome back. Okay, so let's go into the topic. So the topic is impulse and momentum. Let me just switch on the chat and just to see who is in, and chat and a list of people. Lovely. Okay, so impulse and momentum. Definition of momentum and impulse. So momentum is the amount of motion. We say amount of motion. So momentum, as you probably know very well from GCSE, momentum is the amount of motion. It is a vector quantity defined as mass times the velocity of an object. Mass is a scalar, velocity is a vector, so when you multiply a scalar by a vector, you get a vector. Impulse is the change in momentum. So sometimes it's written as I, impulse. I prefer not to use I, so I just use delta P. Delta P, and that's, you can say it's P final minus P initial, or you can say it's MV final minus MU. Okay, so that's impulse. And there's if you write down this, you can carry on. So delta P is MV minus MU. So you can take M out, that's V minus U. And if you get, you can write it as mass times the change in velocity. And if you divide both sides by delta T, you get delta P divided by delta T is equal to mass times delta V divided by delta T. What's delta V over delta T? Change in velocity over change in time. Acceleration, yes, so it's mass times acceleration, and as we already know, mass times acceleration is the resultant force. So, resultant force is equal to change in momentum divided by change in time. This is another way of writing Newton's second law. So this is Newton's second law. So just doing some manipulation. It comes in very useful, and we will be using that. A consequence of that is that the change in momentum is the force multiplied by time. So the impulse is force times the time. Interesting. So, you know what? Let's do an experiment if we can. So, vet forces. Let's see if we can do an experiment. Masses, values, speed. Okay, I think I need a stopwatch because I don't see a stopwatch on here. Hopefully, that gives me okay, so I'm going to use a 200 kilogram mass, And I'm going to push it with a force of 50 newtons for 10 seconds. So how do I do a timer? I'll do a time stopwatch. Okay. I'll do it for 10 seconds. So 3, 2, 1, go. 3, 4, 5, 6, 7, 8, 9, 10. Okay. In 10 seconds, the mass has gained a speed of 2.5 seconds. Okay, so let me see if that makes sense. Right. So delta t is 10 seconds. The force I used was 50 newtons. And the initial velocity was 0 meters per second. The final velocity was 2.5 meters per second. And the mass, of course, is 200 kilograms. So let's do some calculations. Initial momentum E equals PV. What do you mean by E? Sorry. There's a question. No, energy is not PV. You can kinetic energy. Kinetic energy is 1/2 mv squared, but momentum is mv. So if you square both sides, you get momentum squared equals mass squared v squared. Now you divide by m, and you get p squared over m equals mv squared. And then you divide by 2, and you get p squared over 2m is equal to 1/2 mv squared. So kinetic energy can be written as p squared over 2m. So that's another thing. All right, so coming back to our fridge on a skateboard. I mean, how often do you see a fridge on a skateboard? Initial momentum is mass times u, which is 0 kilogram meters per second. The final momentum is mass times v, which is 200 times 2.5, which is 500 kilogram meters per second. Change in momentum delta p is, of course, 500 minus 0. So 500 minus 0, which is 500 kilogram meters per second. Now, and we said that delta p can also be written as force times delta t. So let's calculate force times delta t. Force, which is 50 newtons, times delta t, which is 10 seconds. 50 newtons times 10 seconds is 500 Newton seconds. Ooh, interesting. So we do have a correspondence, and kilogram meters per second is the same as Newton second, so they are equivalent. You can prove that by yourself, but yeah. The change in momentum. Does this make sense? Does this make sense to everyone? So force times the time is equal to the change in momentum. And the change in momentum can be calculated by, well, either force times time or the final momentum minus initial momentum. On a scale of 0 to 10, does that make sense? Please let me know. I want some feedback. Same thing. 9. One person replied. Anyone else? The question was, does it make sense to you on a scale of 0 to 10? Please let me know. I'd like some feedback. Okay. So applying a force changes the momentum of an object. And that change in momentum is called impulse. We say the force delivers an impulse. The force delivered 500 Newton seconds of impulse. The object changed momentum by 500 kilogram meters per second. But Newton second and kilogram meter per second are the same thing. So technically you can use them vice versa, although some exam boards are very, very picky on what you need to use. So for impulse, we tend to use Newton seconds. For momentum, we tend to use kilogram meters per second. Okay. If you want to slow something down, I believe I can stop this in 5 seconds if I use 100 Newton force. So I'm going to do the same thing, but in the opposite direction. And I'm going to push it for 5 seconds with 100 Newton force. So 3, 2, 1, go. 2, 3, 4, 5. Almost. Close. Okay. So I can. Okay. Slightly over the top. So if I push with a bigger force, it will accelerate faster, of course. So I'm delivering more momentum, more impulse, sorry. So force times time is the impulse. So to reduce the momentum, I need to deliver an impulse in the opposite direction. So this slows the fridge down. Okay. Back to the situation. A force changes momentum. So a force changes momentum. Okay. I hope this makes sense. Moving on. Consider 3 objects interacting with one another. Show that in the absence of external forces, the total momentum is conserved. So I can't demonstrate it here, but if you have more than one object and you have no external forces, the momentum is conserved. So that is the principle of conservation of momentum. So let's take 3 objects, M1, M2, and M3. Imagine that these objects interact with one another. We don't know how they interact. It could be a magnetic interaction. It could be an electrostatic interaction. It could be anything. So we will label this as force of 2 on 1. It's the second object pushing the first object with this force. So force on 1 from 2. F 1, 2, it's force on 1 from 2. Does that make sense? So 2 is pulling 1 to the right. But that also means that 1 is pulling 2 to the left. That Newton's third law. And this is F(2)(1). 2 is being pulled by 1. Force of 1 on 2. Sorry, force on 1 from 2. Yes, force on 2 from 1. Imagine that, well, these are vectors, of course. Imagine that these two also interact. M2. Let's say M2 and M3 are repelling. So that's F(2)(3), and this is F(3)(2). And imagine M1 and M3 are being attracted to one another, and the force is F(1)(3), F(3)(1). The force numbers were wrong. Y numbers are wrong. Force on 1 from 2. Force on 2 from 1. Force on 2 from 3. Force on 3 from 2. Force on 3 from 1. Force on 1 from 3. I don't think I made a mistake.
It looks like force 12, force 21, force 23.
21. No, 21 means force on 2 from 1. So you can put a comma if you wish. It's just a double index.
Normally, don't you write one number less inside the force, write one number on the right side of the force?
Oh, it doesn't really matter how you do it. You choose any notation that you wish. You can do a force on 1 from 2. You can write force on 1 from 2 like this. I don't like this notation technically, frankly. So yeah, I hope there's no problem with using this notation. I also imagine that there are 3 external forces. So this is F1 external. This is F2 external. And this is F3 external. So it's an external. We don't know what it is. They're just external forces. So let's write out Newton's second law for each of the masses. So Newton's second law. M1, acceleration 1, the acceleration of mass times acceleration for the first mass is equal to F12 plus F13 plus F1 external. Then for the second mass, I write M2A2 is F21 plus F23 plus F2 external. And for the third mass, similarly, it was F31 plus F32 plus F3 external. And now I'm going to add the 3 equations. So I'm just going to add the 3. So M1A1 plus M2A2 plus M3A3. Is equal to F21, F12, but F12 plus F21, that's 0, because they are opposite. They're opposite, and they have the same force. F13 plus F31 is 0, and F23 and F32 is 0. So what I have is F1 external plus F2 external plus F3 external. Right. I can write it as the sum of external forces. And here I'm going to write m1 delta p1 divided by ma1. So for each acceleration is final velocity minus initial velocity. So acceleration is final minus initial velocity divided by the time taken. And I'm going to write this as m1 v1 minus u1 divided by t plus m2 v2 minus u1 divided by t plus m3 v3 minus u1 u3 divided by t. And I'm going to regroup them. I'm going to group all the v's on the v's and all the u's separately. So it's going to have m1 v1 plus m2 v2 plus m3 v3 minus m1 u1 plus m2 u2 plus m3 u3 all over t equals the sum of external forces. Okay, what is this expression? What is this expression? It's the total momentum at the end. It's the total final momentum. So P total final minus P total. This is the total initial momentum. Total initial momentum. And is sum of the external forces multiplied by the time of interaction. Time is, of course, the same. So we can write it as delta P, the change in momentum. Change in total momentum is the sum of external forces times T. And this is an important result. So if the sum of external forces is 0, then delta P is 0. The total change in momentum is 0. So this is conservation of momentum. Momentum is conserved if the external forces, if the sum of the external forces are 0. If time of interaction is 0, then the change in momentum is 0. This is a situation in a collision where you have a very swift collision. So example, a collision where it happens so quickly, so where t is so small that momentum doesn't have enough is very small. So the total momentum does not change in a collision, for example, between two automobiles. The time is very small, so we just don't have time for the external forces to cause a significant change in momentum. And if each external force is 0, then the change in momentum is 0. So in A level, you are required to recall that in an isolated system, the total momentum remains the same. An isolated system means the sum of the external forces is 0. Okay. Hope that makes sense. Do you think you were able to follow my explanation on a scale of 0 to 10? Please let me know. Do you think you were following the explanation? Cool. If you didn't manage to follow the explanation, do you think you managed to understand the consequence? That the total moment, the change in total momentum is 0 if there are no external forces. The internal forces cannot change the total momentum. That's another consequence. Internal forces do not change. So internal forces do not change total momentum. Okay. Okay, problem 3. This is an Isaac physics question. I am stranded, stationary in space, but near to the spacecraft. Okay, so an astronaut is stationary. The spacecraft, I want to draw a rocket. Most spacecraft do not look like rockets, but whatever. So this is the spacecraft. This is the astronaut. So there's no friction. There's no way you can get to the spacecraft. So the astronaut detaches a 30-kilogram cylinder of oxygen and flings it from the spacecraft at a speed of 3 meters per second. The mass is 80 kilograms. This is 30 kilograms. And as a result, because the astronaut pushes the cylinder, Newton's third law says that the cylinder will push the astronaut. So the astronaut will travel in the opposite direction. So this is an example of an explosion. So this is an explosion where you have two pieces traveling in opposite direction from stationary. So initial momentum. The momentum of the 1 plus momentum 2, well, it's going to be 0 because the astronaut is stationary and so 1 is the cylinder, and 2 is the astronaut. Okay. So total momentum is 0. So both stationary. Now finally, final momentum. So the oxygen, or the oxygen balloon, so P1 dash plus P2 dash, well, it has to be also 0 because it's conserved. So P1 is minus 3 times minus 30 times minus 3. So it's the oxygen cylinder traveling to the left plus the astronaut, so 80 times V, And that has to equal to 0 because it has to equal to the initial momentum. So momentum is conserved. I like to write the conservation of momentum like this. P1 plus P2 equals P1 final plus P2 final. That's how I write it. I'll do this in a minute. So let's just calculate. Well, no, let's do it like this. So initial momentum is 0 plus 0 equals final momentum is minus 30 times minus 3 plus 80 times v. So initial, final. Okay, I hope that makes sense. And that's 0 equals minus 90 plus 80 v. So v is 90 over 80. So it's approximately 1.125 meters a second, I believe. Yeah, meters per second. Okay, so that's how the astronaut can reach the spacecraft by flinging the cylinder. What would be a better solution? What would be a better solution for the astronaut? And why would this solution not be good? Let's fantasize a little bit. What could go wrong? What could go wrong? What if the astronaut flings it slightly in the wrong direction, like 20 degrees wrong? So, well, yes, you need oxygen, of course, assuming there's a little bit of oxygen left in the spacesuit. I don't know, or maybe there's an extra tank. The astronaut cannot breathe. Yeah, that would be an obvious one. Probably they have another tank, another cylinder. But if you fling the cylinder in the wrong direction, you will travel in the wrong direction. Well, yeah, you can miss it. And you only have one, you don't have many cylinders to correct your direction. So you fling it, you missed it, and you'll never reach it. You'll never reach the spaceship. What would be a better solution if you have an oxygen tank? He could, or she could, rather than, open the oxygen tank. So open the oxygen tank, like, and use it as a jet. So the jet of the oxygen would travel at incredibly high velocity because there's no air resistance. So the oxygen would travel to the left, and the astronaut with the tank would travel to the right. And the beautiful thing about it is that you could control the direction, and you just open it a little bit, you travel, then you adjust just like a rocket does. So gas goes left, astronaut and cylinder. Astronaut goes right. Not only you could change the direction, you could also stop yourself using the oxygen tank. So it would look something like this. So You can push it, oop, stop pushing, it travels, and then you push it in the opposite direction and you can make it stop. So that's the equivalent of pushing yourself against the oxygen in the tank. Okay, moving on. A male and female skater of equal mass are moving as shown in the figure. This is another Isaac physics problem. The female skater is moving at a speed UA at an angle of 45 degrees, 5 degrees, and the male skater is moving at the speed at 45, so 45 degrees. Same speed. When they collide, they cling to each other and both move horizontally with velocity v. Okay. Well, first of all, we need to find v. So v is question mark. You need to write down conservation of momentum. And here is an example where you need to do it both vertically and horizontally. Vertically. This is in the y direction and this is in the x direction. So vertical momentum. And once again, I'm going to write P1x, P1y, that's vertical, plus P2y equals P1y final plus P2y final. So y means vertical, 1 means, well, A, B, A, B. Okay. So the vertical momentum of the first object is minus m multiplied by UA times sine 45 degrees plus MB, so it's M multiplied by UB multiplied by sine 45 degrees. So it's the vertical component of the velocity. Sine, let me use theta for now. Sine theta, sine phi. And that is equal to, well, you will see that it has to be 0 because they are moving horizontally. Okay, so let's substitute what we know. So sine 45 is square root of 2 over 2. So m minus m UA square root of 2 over 2 plus m UB square root of 2 over 2. And it says that UA is equal to UB. So yeah, it makes sense. So since UA equals UB, this is true. It's true. Not really useful, but it is true. Now we look at horizontal momentum. Horizontal momentum. So once again, PAX plus PBX equals PAX dash plus PBX dash. So PAX, so that's M times UA cos theta plus PBX M UB cos phi equals, now they're both moving at the same velocity, so it's MAV plus MBV. Okay, cos square root of 2 over 2, so that's UA, so MUA square root of 2 over 2 plus MU, they have the same velocity, so UA square root of 2 over 2 equals 2 MV. You can add these two, so 2 goes away. So MUA is equal to root 2. Oh, what? MUA root 2 equals 2MV. M cancels, and then V is UA square root of 2 divided by 2, which is UA divided by square root of 2. So the final velocity is square root of 2 times smaller than the initial velocity. That's the answer. You might say I've overcomplicated things, but hopefully I've shown you the method I prefer to use. You don't have to use this method, but this is my preferred method. Okay, talking about the same male and female skaters, but this time the female skater is moving at the speed AU at an angle theta, and we know that sine theta is 1/3, so theta is arc sine 1/3 below the horizontal, and the male skater is moving half the speed, so UB is UA over 2 by modulus, of course. They cling to each other and both move horizontally. Okay, so if they move off horizontally, that means that their vertical momentum, vertical. All right, so MA is moving down, so minus MA UA sine theta plus MB UB sine phi, and that has to equal to 0. Has to equal to 0 because they move off horizontally. So the total vertical momentum is 0. Let's substitute what we know. We know that UB is 1/2 UA, and we know that sine theta is 1/3. So we can divide by mass because they have the same mass. So minus UA multiplied by 1/3 plus UB, which is 1/2 UA sine phi equals 0. So sine phi is 2/3 from here. Phi is 2/3. Sine phi, it is 2/3. What is V in terms of UA? So now we'll look at the horizontal momentum, and we have MA UA X, well, the horizontal, which is UA cos theta, plus MB UB cos phi equal to 2m. They have the mass, 2m, and here, I don't need m, a, and b. They have the same mass. I'm just using m. 2m v. So I can cancel the m's, and UA times cos theta. Well, sine theta is 1/3, so we can calculate cos theta. Cos theta is the square root of 1 minus sine squared theta. I'm not using plus minus because, well, it's an acute angle, so it's obviously plus. So that's going to be 1 minus a third, so a ninth, so 2 root 2 over 3. Yikes. Yeah, it doesn't look good. And cos phi, that's 4 ninths, so 5 root 5 over 3. So I can substitute that in. So UA multiplied by cos theta, which is 2 root 2 over 3, plus UB, which is 1/2 UA, multiplied by root 5 over 3, equals 2V. And I can write that V is equal to UA multiplied by 2 root 2 over 3 plus root 5 over 6 all over 2. Can I simplify that? It's UA 2 4 root 2 plus root 5 over 12. Okay, something like that. Excellent. I have one last question that it is something you probably haven't seen before. It's a tough one, and it is almost identical to one of the questions from the assignment. So let me show you which question I am referring to. Problem 14, the double star question. A bag of sand is thrown out of a window and lands on a horizontal street without bouncing. Okay. So a bag of sand slides down a frictionless ramp. And this is smooth. And this is rough. When it hits the rough surface, it stops immediately. So you need to find the angle, theta, is question mark. Okay, interesting. So let's try to figure out what's going on. Like, what's causing it to stop? Yeah, the friction force, of course. The friction force. And what is the friction force equal to? Because look, the normal time, normal times the coefficient of friction. Let's look at the friction situation. So there's a friction force, and masses, friction. So let's say we have lots of friction. We push the mass. It's going, going, going. Now I stop pushing, but it doesn't stop immediately. There's a constant friction force which slows it down, but it doesn't stop immediately. How does that even work? Like, it slows down, slows down, slows down, slows down. So it's already moving. It's already moving. And somehow the friction force is so large that it just stops. You've done lots of questions on friction. That's not how friction works, right? So it's sliding down a ramp. So by the time it slides down a ramp, it has a velocity. It has a horizontal velocity. And if you have a horizontal velocity, the friction is mu n, mu times the reaction force, and your acceleration is the force. It's mu n divided by your mass, where m is the mass, and then the time to stop is your initial velocity, initial horizontal velocity, divided by acceleration, which is Vx divided by mu n times m, which is definitely not zero. You don't stop instantly. So you will slide for some time before stopping. What is going on? I'm going to ask a question. Does n equal mg? What do you think? Yes or no? No, when it's on the horizontal floor. When it hits the horizontal floor. That's what we that's the problem that we're facing. We assume that n is equal to mg. True when moving along the horizontal floor. But not true where at the moment when the bag hits the ground. At the moment when the bag hits the ground, n is many times bigger than gravity. And it has to be so. You can stand on the ground, normal reaction is equal to weight, perfectly fine. If you try jumping from the second floor, you will probably damage something because the normal reaction force becomes so much bigger the moment when you land. Does that make sense? When landing. And we have to take that into account. We have to take that into account. So the normal reaction force, as a matter of fact, through time, when it hits the ground, it goes huge. and then it reduces to when it reduces to mg. Okay, that's why this problem is so difficult. That's why it has 2 stars. It's a dynamic situation. You have a hit, which is a really large force, and then relax. So hit and then force drops down. So when it hits the ground, there's the normal reaction force, which is really large. And there's a friction force, which is mu n. Okay. Now, assuming that it is traveling at a horizontal velocity, and let's say just before it hits, it's a velocity before it hits is v. So horizontal, so vx is v divided by root 2, and vy, oh sorry, what am I saying? Vx is v cos theta, and vy is v sine theta. Assume the bag stops in time delta t. In time delta t. So oh yeah, so delta px, the change in the vertical momentum is mv cos theta, and delta py is mv sine theta. Assume the bag stops in time delta t. So for the horizontal force is mu n, and it acts for time delta t. So mu n times delta t. So assume the collision with the floor lasts for a delta t seconds. So it's a very short period of time. And the impulse delivered is mu n times delta t. And that's equal to delta px, which is mv cos theta. The vertical momentum, vertical force, is n. So we ignore gravity because n is many times more than gravity. So n times delta t, the normal reaction times the time, is the change in the horizontal momentum, which is equal to mv sine theta. And from here, I can express n delta t is equal to mv sine theta, and I can substitute that into here. And what I get is mu multiplied by mv sine theta equals mv cos theta. Mv cancels, and I get mu has to be, tan theta is equal to 1 over mu. In other words, theta has to be greater or equal arctan 1 over mu, which is arctan 1 divided by 0.7, which is, am I in radians? I don't want radians, degrees. Arctan 1 over 0.7. 55 degrees. 55 degrees. Amazing. Okay, so once again, before hitting the ground, let me just walk you through. Before hitting the ground, the bag has horizontal and vertical momentum. Before hitting the ground, so summary. Before hitting the ground, bag has vertical and horizontal momentum. Horizontal momentum. The vertical momentum is removed by n, and horizontal momentum is removed by the horizontal force, which is mu n. In time delta t, which is very small. So n times delta t is equal to change in py, and mu n delta t is the change in px. And then the change in py, we know the change in py is mv sine theta, and change in px is mv cos theta. And then you substitute that into this one, so it's mu. So you substitute this into here, mu mv sine theta equals mv cos theta, and the rest is history. Does that make sense? Have you managed to follow my explanation? So the bag is traveling like this. There are two forces, N and mu N. We ignore mg because mg is very small compared to N. Mg is many times smaller than N, so we ignore mg. Okay. Any questions? I hope I haven't left you completely baffled with this one. I have done multiple webinars on this topic, so please watch my old webinars from last year and the year before and the year before. So it's the fourth time I'm doing this topic. So you have a whole 3 webinars that you can watch. Okay. All right. I'll finish here. I hope this was useful to you, and I'll see you next week for some integration. Okay. All right. So see you, everyone. Enjoy doing the assignment. Okay. Bye.